We're from FTC Team 6699 Tempest. Tempest is a 3-year-old veteran FTC team. In 2013 to 2014, we were the Inspire Awards state winners. We hold several awards at qualifier level, and we were at state last year. But today we're going to be talking about electrical faults, they're very common. We see them a lot at competitions. They're almost always preventable, but they can cost you your match. They can cost you parts of your robot. What you want to do is you want to build good habits so that these tips can become second nature. All right, so we're going to start with wiring.
Also, if you guys have any questions, just raise your hand.
Yeah. So one thing that has happened to us is human error. So what we like to do is color code our wires. For example, have red be positive and black be your ground wire. This can reduce the risk of accidentally shorting a system. Now, this is from experience. We did short out right before a match when we were replacing a wire. So you do want to keep a lot of extra red and black wires just in case you run out of a certain color.
Yeah, we fried a motor controller because we ran out of red wires, so we used black wires for power and ground, and we destroyed a controller, and so we were frantically trying to find another one.
Yeah. So organizational tools can reduce the chance of shortages and just messing up. One thing we personally do is we drill holes in our robot to route wires through your robot to keep your wires away from your moving components so they don't get snagged. We also use a lot of electrical tape and zip ties. One thing we've noticed in more recent years is that teams have been using more tubing and channels to route wires through their robot, and this again can help reduce the chances of things getting snagged.
So, for example, our robot, we had a giant gear mechanism that if anything got caught in it, it would just destroy any wires. So behind all that, we had Tetrix bars that we just wired all of our wires through, motors and power, and we had no problems with snagging internally.
Yeah. So, and then keep like with like, so route power motors and, power and ground with each other and then motors near each other. Okay. So, shorts. So, the most likely place we think for a short to occur is in a connection with a legacy controller. By that we mean the old controllers. So again, color coding can help with this, but it's not really a solution. So what you want to do is make sure the bare wire isn't frayed, if it's not too long, if it's not in fully. The positive and ground wires can actually come in contact with each other and cause a short. So what you want to do is cut your wires so you can't see any of the metal and crimp them well. And then, of course, the other place for a short to occur is at a splice. This can happen if you're splicing your wires together using something like electrical tape, where it can come undone and the wires again can come into contact and cause a short. So to avoid this, we would use one of these 3 techniques. The picture in the middle is a wing nut. Just put the wires in the nut and twist it. The one on the left is a lever connector. That's the one we actually use on our robot, and that's very easy to use as well. You just insert the wires in the hole and then you close the lever. And then if you want something that's permanent, you would solder your wires. So I think the veteran FTC teams know this, but your battery is very important and you want to keep it inside your robot at all times. It seems simple, but when your robot is actually moving around, the battery can get jostled and you don't want it to become unconnected. So we would recommend switching your connection to the Anderson power pole stuff since it's more reliable. And when you're focusing on designing your robot, make sure to put it someplace where the battery can fall out. So the picture on the left, that's Anderson power pole connectors, and we actually use basic Tetrix pieces to hold it in, just kind of box the battery in. So, of course, everyone knows the phone, it's the new upgrade for next year. The micro USB ports on the phone are notoriously bad, so what you want to do is protect your micro USB ports to hopefully keep on using the same phone for more than a year. So we came up with a couple of mounting ideas. We would recommend using 3M Dual Lock, 3D printing a custom mount, or I saw some teams experimenting with Tetrix pieces and zip ties on Twitter as well, so that could be another idea.
3M Dual Lock is kind of like Velcro, except both sides actually will connect with each other. So like in traditional Velcro, you have one side that's loops and one side that's hooks. In the Dual Lock, both sides are hooks and loops, and so it's extremely strong. And you have to try really hard to actually pull anything out of there.
Alright, and to secure your phone cord, we would use simple things like electrical tape or zip ties. You could come up with something that's a little bit more complicated, but that's what I think we'll be using next year. And then we would recommend using the tubes from Tetrix to protect your cord from getting snagged on anything. So.
All right. So getting into some more of the wiring methods. I'm assuming a lot of teams here will still be using the black controllers that need to get power out from a singular source. So a solution that we have is if one of your controllers comes on down with the power, if you have it in the normal sequence, then the rest of the controllers in line will not receive any more power. But if you do a parallel connection, like this diagram here, even if the very first controller gets disconnected at the power source, so right here, you'll notice that all three of the other controllers will still be intact. So the boxes here are supposed to be the lever connectors, and so the only way to actually disconnect these, you'd have to cut off this wire or the source wire. And so your traditional just sort of sequence, the wires would go straight from this controller to the next one. So if this controller comes in power, all the rest would. But a lot of teams will be getting the new systems, and that sort of deals with a lot of these issues. So the new electrical systems, there are a lot of new components. This is a core power distribution module, and the reason that this takes care of that issue with parallel circuits rather than a sequence is that it takes care of all the parallel wiring in that diagram internally. And so the core power distribution module has 6 outputs that all have 12 volts, and it also has 7 USB connections in the back. And so you do all of your data and power management all through this one controller. And even if you unplug one of those power connectors or the USB connectors, the rest of the system will still work perfectly fine. Some of the new controllers that are coming out these are the basic motor and servo controllers. They're essentially the same as the black ones, the older ones, except you'll notice that they all use Anderson power pole rather than the screw down connections for both the motor and the power connectors. And they use USB data lines rather than the I2C, which is can be a little bit of an issue since it's a USB connection. But besides that, they operate the same. 2 new systems that are fairly different than what we've seen before are the core device interface module. And so this is just allows you to add on your own servos or your own sensors. It has I2C, analog, digital, and pulse width modulated interfaces. So if there's a sensor that you want to connect, you can basically connect it to that. And the connections in there are kind of like the servo connections on the servo controllers, and those are pretty strong. And so it has a USB input for all the data, like all the others. And then the one at the bottom there is the core legacy module. And so that is what's going to allow you to connect your old controllers and your old sensors that even second-year teams will still have. And so, one thing with the core legacy module is that you can't daisy chain all of your controllers, like last year with the MXC brick. I've read that it theoretically can do it, it's supported in the hardware, but the SDK by Qualcomm doesn't support it. And so if you want to connect more controllers with a whole bunch of old sensors, you just buy 2 of those, and it should work. And so these new connections and means of data transmission pose some new issues that we haven't seen before in how to actually set up your controllers. And so the USB ports, especially USB type A or B, have always been pretty bad, especially for how many unplug and plug cycles they have. Your basic USB port can be plugged in about 5,000 times before it should fail. Some USB ports are only rated about 1,500 times. And so to protect your USB connections and not have to force you to buy a whole new controller, put as little tension on it as possible, both perpendicular to the connection and parallel to it, because it's super easy just to bend, especially the micro connections. It's really easy just to break those. And leave them plugged in as much as possible, or unplugged as much as possible. Don't be switching out your cords all the time, because it'll just wear down the port. And so just hide those actual connections from external interference or even internal interference, because if they get, it takes very little force to break USB connections. And so the one good thing about the new controllers is that they use power pull rather than the screw down. And so your chances of shorting out on the power input is very small, because it's all contained within those plastic shields rather than the screw downs. And then the actual servo and encoder connections are basically the same, but I've never seen really any issues with those connections before. And then the other thing with the new motor controllers is that they don't have LEDs, from what I can tell. They might have them internally, but I'm guessing that they don't. So the black controllers before would have a red LED that turn on when they actually are receiving power. So one way to sort of get the same effect and debug issues really quickly is if you put a red LED or whatever LED you want in line, you can tell if a controller is actually getting power. So in this specific case, you have a red LED and then you put a 560 ohm resistor in there. You won't drain your battery, but the LED won't burn out. And so if you want different colors, like if you want blue or something, it's really easy to connect, to look up what resistance you want. So you got that URL, or there's an electrical that will handle that. So moving on from general wiring, we go into motor and servo electrical. So a motor connection, so the Tetrix motors have those hubs on the back, and those are pretty weak, and they can get broken really easily. And so some teams have had really good setups where they use like 3D printed stuff, and they got awards for that even, and it works really well. But if you don't have that amount of time to invest to protecting your connection, what we do, and it's worked for us the whole time, is we take electrical tape and just strap it to the sides of the motor and have it go around the back of that hub. Your connection will stay on fairly reliably. We haven't run into too many issues with that. But of course, if you have like a whole plastic shield, that would probably work better. And then for your servos, make sure that you have a good brace in there. When I was in 8th grade, so about 4 years ago, we had a robot that had sort of a manipulative arm that would grab the boxes from bowled over. And it broke twice within about 2 matches because we didn't use the braces. And so if you put those, it's like, it's just from Tetrix. If you put that around there, you're taking the strain off of the actual axle. So like, if you put a perpendicular strain to the axle, it's going into the brace rather than the servo. So the servo is only doing rotational force. So you save servos and save money. You won't have to fix your robot. So just use the braces. So 2 years ago, the year that we went to Super Regionals, we had a huge issue where our motors were just breaking left and right. I think we had like 5 broken motors or something. It was horrible. And so this is a super important issue, and we got a lot of experience diagnosing motors. And so there are 2 main things that we saw that would actually break in a motor. The gearbox in the front, some of the gears in there will just break due to it being old, or it has too much extra force put onto it. And so if that breaks, you can still sort of save the motor. But then in the back part of the motor, where the actual electrical components are, there's a resistor that we saw on 3 of our motors break. And so if that's broken, you can't really replace it because you'd be modifying electronics at that point, which is illegal. And so the gearbox on the front is replaceable. And then the resistor, you could take it back off and replace it if you want like a test motor, but you can never use it in competition. And so I looked at some of the schematics for this motor and what it's rated at, and tried to diagnose why are all my motors breaking. And so theoretically, the Tetrix motors are rated for 6 to 14 volts, but they did all, as you can see on the test of their schematics, they ran all of their tests at 12 volts. So Tetrix is saying you need to run these motors at 12 volts. And so the battery, if you look at the 12 volt battery from Tetrix, at a full charge it will actually output 14 volts. And so what we were doing is we wanted the robot to go as fast as possible, so we just pushed 100% power into our drive motors, which means we were pushing 14 volts at a max battery charge. And so if we ran into something and our wheels aren't turning anymore, the motor would just take all of that electrical force internally and break all of these resistors over there. And so we don't even know what resistance these resistors were or anything, so we could not fix these. And to actually pop that back off, we had to completely destroy the housing of the motor. We took a file and shaved down the aluminum on the outside just to see what was causing the problem. And so, to fix this, what conditions you need to take are make sure your motor doesn't stall. So you can do this by gearing up your motor so it's harder for it to stall out and has more torque and your wheels will keep spinning more often. Or put in a sort of like a kill command that if you know that your motors aren't turning for a few seconds, just stop them and save them. And then the other thing that we do, and it works really well even if like there was an autonomous where the robot was completely bugged out and it was just hitting the wall for the 30 seconds of autonomous and taking all that force internally. But our motors are actually fine after that mesh because I reduced the maximum voltage they could get to 12 volts. And so the way to do that in the new Java language is set the maximum power that the motor can ever receive to 12 over 14. And so that will give you the appropriate amount of percentage of power that you can possibly have. So just keep in mind, make sure you can't push your motors to the limit, and otherwise you'll just break them. So if you do happen to break a motor, which we have done a lot, there's a few things you should first do. So just hook the motor up and run it on its own. If you don't hear any sounds, make sure it's actually getting power and it actually should be running before I just say it's trash. So if it does make a sound, if there's a clicking or a humming, if it's clicking, then one of the gears in the gearbox is broken and it's skipping. And then when it skips, it will just continue on turning. So you can use a motor. If it is clicking, you can use that motor still, but it won't be very good. If you hear a hum, that means the connection from the motor to the actual gearbox is not reaching anything, and it's just spinning internally and not going through the gearbox. If you still don't hear any sound, and you know it's getting power, then that motor is good to throw away, because that means that the resistor in the actual motor part is broken,